Hi, welcome to the lab. In the last video, we implemented, so let me start differently maybe. So we are currently working on a scanner generator library, and we specified tokens in this way. So we have different kinds of tokens. First of all, we have tokens I'm calling literal token, which are matched exactly in the input text. And you give it a token name, and in this case, a literal string. So this is a symbol, but also the keywords are literal tokens. Some tokens, however, such as identifiers, literals, or white spaces, you specify by providing a regular expression. And out of those token specifications, basically, we construct first of all, for each of those patterns, we construct a single automaton which detects this single token, and then we combine everything in one big automaton. And so this is basically the state of the project where we left off. And yeah, we did some shortcuts, and I'm going to clean up a little bit now. So first of all, I noticed that I stopped executing my tests. So let's introduce this call again to our small test framework and run again. And we should also see how the combined automaton looks like. So here, basically, this is the automaton for the whole, for every possible token that I'm specifying here. For example, let's find an interesting pattern. For example, I should somewhere match identifier, but I'm not really. So we have here some signs of identifier. So it seems like that this state 12, matches identifier. So let's experiment a bit. So I know there is the GraphWiz tool. Maybe this can help us not manually having to draw this the graphs. But this is not what I want to do today. Maybe I will check this out, and yeah. So because this is quite messy, and I don't want to draw every graph, every automaton myself. So yeah. But today I'm just wanting to clean up our internal data structure. So this is a little. I think it's boring. First of all, let's remember what I just said. So visualize so what I wanted to do is the following thing. I'm currently using the same data structure for representing non-deterministic finite automatons and deterministic ones. And I don't really like this, since, for example, non-deterministic finite automatons can have epsilon transitions. The transitions can be marked with an epsilon, and then you can spuriously transfer a transition from one state to the next one. And I would like to have a clean data structure that does not allow this. And also our NFA, the arc can either have an epsilon transition or a character set. And so this is just internal, and I have some assertions that I would like to get rid of. So maybe let's start with this. So I would like to create a small enum class. I'm just calling type. And I'm just differentiating between an epsilon transition and a character set. And so we don't need to remember. So I think we will just do something like this. Of course, we then have to also remember our type. So now let's move this at the top. And type. Okay. So let's fix all compile errors. There should be a few now. So now I'm thinking to split this into two cases. I would like to have two methods, one for create epsilon. So this is the method you use for an epsilon transition. But also there's another one which is called create, char set. Transition character transition. Character arc sounds like a chapter in a book. And we're just passing it a character set. And we default to the empty character set here so that I can leave it out and fill it out later. So thinking of just implementing this. Just doing those changes now. So we have an epsilon. Epsilon. And then of course we pass it a arc type epsilon. We pass it the type and also the other method, character arc. Clean this up. And this is basically the same code, except we're flagging this one as a char set. And also we are adding the char set we are given as a parameter. We also assign this. So now we will get new problems. So arc epsilon, this is not really the case. It's not really possible anymore with this. But I think I will reintroduce this. So our arc knows its type. Let's just introduce, so those are the members. Let's reintroduce some helper methods. So this epsilon, and this just checks the type, the underlying type. So type epsilon is type epsilon. What? Oh, yes, like this. And maybe is epsilon and is character transition. Okay. Okay, so then I can here ask if this is an epsilon transition. So let's see. Sure, now this one is an epsilon arc, and I think we don't need this helper method anymore, since we have a direct auxiliary function for that. So epsilon arc is now called automaton create epsilon. Okay. And once again, so this create arc is just create character arc, and we pass it the expressions character set. So this is now a lot cleaner. Don't need to have an external method. It's an operation on our thing. So, and this one, of course, is when we're creating the NFA. So this one is just the singleton character arc. So in this, just change this one to character arc, and I don't need to remember this anymore. So now, of course, this was the whole reason this assert can now go away. One can ask this epsilon here, and this one also, I can also, wait, if not epsilon, so if we're looking at a character transition, yeah, we are here finding all states reachable by epsilon, so we are skipping the character transitions. Similar here, we can remove the assert, and here we see if we are reachable by a given character. So we just, if we are an epsilon transition, we skip this. This arc doesn't describe what we care about. Okay, sure, and then I think this should almost be it. And here, this is a great arc for a DFA. So doesn't matter, I'm fixing it also. So create character, and then I'm passing in a char set with my character, which is C in this case. And it doesn't matter if I set it again, since the character set is a set of characters representation. So it's not memory efficient, but efficient because it only can hold characters. Okay, sure. So perfect. Now I think I did one step of my refactoring. Let's see if it still runs. Okay, I still get an automaton and every test. So I'm also running the tests. Where are those? Oh, I have a main somewhere here. So I'm also running my tests on every execution. So what did we do? Basically, we made epsilon and character sets epsilon. Somehow the word looks wrong, but I think it's correct. So we made them mutually exclusive. So you can still zap them, but basically I think we don't need. Oh, let's try this. make, let's just first commit, make sigil, make sigil arc either epsilon or I think you can still fudge it, but so for example you could like here, and I'm doing this, and find an arc, and you get an arc. Wait, character arc. Ah, yeah. So we find an arc with 2 nodes, and we can still manipulate the underlying character set manually. But so this will change eventually, since I'm going to introduce 2 different data structures for DFAs and NFAs. So let's do this now, I think. So I think I'm just going to use very similar structure. So let's just copy the class. Good old copy and paste. What's your problem? Let's do it in the file. Somehow I would have expected that you just can. Where can I open this in my Explorer? Open Explorer, thanks. So just copy the classes. Let's just make them compile. So DFA. Oops. So this namespace is called DFA. It has the same capabilities basically with a state, which has an ID. It knows that if it's started, it knows if it's accepting. But instead of this one, it can either be accepting or an error state. So I'm thinking I'm just modeling what I want to press here. So we create a enum class for the type, and this is a error state or an accepting state. So this is the type of the character. I think I won't pass this in, I think. And let's also introduce another type, which is called invalid, that we have a dummy value for initialization. So, and then arc can't be an epsilon anymore, so I don't need differentiation here. No, I don't need this, I don't need this, but I still need everything here. So, and this stays the same. And here we only have a single create arc, and we also pass in an initial character set. And the format method, let's just drop this for now. So now the DFA class, let's fix everything. I included the wrong header. So let's see. This method is gone. One is just called create arc. We don't need to differentiate more. So It's also introduced some helper methods like Boolean is accepting, and also is error state. And then I can ask is accepting here, or just to fix the log method, and accepting a DFA automaton, and then this is not possible anymore. We can't have an epsilon state. So I think we can simplify this a bit. But now this method is a little bit weird. So thinking to move this directly to its own logger instance. So let's create a template specialization for our formatter for our DFA. Of course, called sigil DFA formatting. I think the method is now called format. Let's double check. Yeah, it's called format. It takes a string builder and the value. Okay. So string builder and the value to log. So an automaton in my case. Yeah. Okay. A const reference. Okay, sure. And now to implement this, we're just going to namespace open namespace core and just implement this method. So can generate a method. Thanks. I don't know why it not completely generate the signature, but fine, I guess. So we have the string builder and the automaton. Yeah. So I just move the code here now. This whole code. Yeah, just work. And now I will also steal helper methods. Here. Well, this one is now a DFA, a sigil DFA state. So now let's also print error states. Is error state, so if we are an error state, let's just print an exclamation point. So for example, if our start state will be an error state, then we print it as like an ID and then the error, so an exclamation point. Or let's say, yeah, so I think it just means, yeah, let's just use an exclamation point for this. So, and of course, this is not case, we don't have error cases in our NFA since by construction they are fine. So now we have a different data structure. Let's also do the following. So the same refactoring basically. We introduce a template specialization. NFA, now we are in non-deterministic land. And now the method is called format, and we format into a string builder. and we get an instance of an NFA. We get an NFA instance. So like this. Yeah, okay. Sure. Now, yeah, okay, why did it generate my method signature? Fine. So let's implement this specialization. So living in the core namespace, and we call this B and this one automaton. And let's just copy paste everything here to here. Also yoink stepper methods. So those. So this was the same refactoring we basically did with the DFA, the NFA. So what's your problem? It's called format. Sure. Okay, cool. Now we should get a compile error. So static format methods, I used them previously. Yeah, so this hack. So basically, let's uncomment this code. I think we should now be able to do the following. So we're just printing the automaton directly. So this was previously not really possible, but I think this should work now. So in this case, of course, we just debug print our DFA. I think this refactoring also, I hope it fixed the bug. Let's try it. Okay, like it worked. So this refactoring also fixed the bug. So let's commit this first, maybe. Yeah, so let's not print this automaton every time. So first things first. What did we do? We refactored the formatter. So let's try to commit the formatting code first. So formatter. Did I remove it? No, this method doesn't exist anymore, so I can remove its declaration. So this is all related. So basically, define specialization of logger for NFA or automaton instead of static method. Let's try to shorten our message. Instead of static method. So previously we had a problem we worked around where every instance was copied in order to print it out. Now, since we know perfect forwarding, this is no longer a problem. So now we can actually use our logging mechanism to log NFA automatons instead of using a static method as a workaround. Workaround, okay. So, perfect. So now let's change the DFA code. So, let's see. So create NFA, fine. This is okay. So now let's see. This is a DFA state. So let's actually use its new type we introduced. So let's also include DFA. So let's see. Let's first change the type. So this struct represents a DFA state. It associates a set of NFA states with a DFA state. So those are NFA states. Those remain NFA prefixed things. One I can keep. I could also inline this method. It's only used twice, but and I could also do something like this. So this is a predicate. And call this one predicate. Also say and predicate arc. And then I'm just going to no. This is actually stupid. Let's just keep it. Okay. So let's see. This is still a DFA state. Perfect. This one operates on NFA states. This is okay. This one also operates on NFA states. But I think I can. So this one is a DFA state. This stays like this. But this one, where is this automaton? Where does this automaton come from? This DFA must be of course, a DFA now. So DFA, let's change it and see where it breaks. So this DFA, whenever we create a state, this one is now a DFA state. Flag it as a start state. This one still fine. We actually have compile errors. Yeah, we do. So so this one operates on DFA arcs. Arc between those two, and we can remember this. We can still do this. But this method is called create arc. Just create arc. I think everything falls in really nicely, falls into places. Here, yeah, I see. So now we are not accepting. We can't just say accepting, but we can say if a state type accepting. So, and also we have to change the result type since we now get a DFA back. But this one still falls into place. So the result is a DFA and we know how to print DFAs. So let's just compile this and see what happens. So I think it still works. Clearly see that this one doesn't work. So every state is an accepting, and each state is an error state. So this doesn't really work. So let's see where this problem occurs. So when we create an so I see this is a copy-paste error. You probably saw that earlier. Oh. So no state. So is this correct? That every state is accepting. I don't know if this state should be accepting. Honest. So let's see. Where do we flag it as accepting? I see. So basically, I did it wrong. So basically, if this contains accepting is set, then we set accepting. Else we set. I think we just set invalid again. So now, of course, this should work again. Okay. Now, not every state is accepting. Still, a lot of states are accepting here. Don't really know if this is correct. Well, it could be, since we know how to try a lot of tokens. So let's move optionality. So I'm just nuking those two tokens for now, and then the first state should not be accepting. Yeah, okay, so this works. So it could be the case that every state was accepting. So, and of course, one is our error state, which we currently don't flag. So let's see. So let's see where this happens. So basically, we did this different data structure for DFA. We did this. This one we need to do next. So fix it. Yeah, so this one we can already do. So we find out. So basically, we can do the following thing. So do we have the reachable set? Still have the reachable set? Don't. Where do we create our state? Here. Here. So state. If reachable is empty, doesn't exist yet, then we set the state to error. So this is an error state. And then we continue. So arc between, fine. Fine. So this new state. So this means that our state is already marked. So if our DFA state is already made, so we look at the state, the type is already set to error, then we keep it. And then we don't have to look state of accepting. And every other case, if it is not is not error, then we look if the state is accepting. So I think we can also do it the other way around. So we don't need this field, but we just let's just create a local alias type. No, I can just do it here. So I don't have to retype the whole thing locally. So then I can just say, so the state type, let's just initialize it with invalid. And in this case, I'm just assigning accepting. So, and then I can just assign the state type and don't need the ternary operator here. So, but we only do this if our type is not yet set to error. So I think now this to-do is also done. Yeah, of course, I don't have a set.isEmpty method. So that's this. Let's add it. So set, how does our list does it? So is empty, non-empty. So, and now I'm just delegating to our underlying list. So size and also for everything else. So empty, also mlist non-empty. Oh, and of course I have to assign, not compare here. So now, I think now our error state should be marked as such. So let's check. Okay, and it is. So state 1 is marked with an exclamation point, which means it is our error state. So perfect. We have a visual representation in our printout. So I like this. So let's commit. Let's just do the set commit separately. Produce a separate data structure for DFAs. So previously, we used the same data structure for NFAs and DFA. We didn't like this because, for example, DFAs don't have epsilon transitions, However, our data structure had a flag for that nonetheless. Nevertheless. Now, since let's say another thing also. Also, the concept of an error state makes no on NFAs, since by construction they can't have error states. So using separate data structures allows us separate, already used separate in the sentence, distinguish between the automaton's capability. Okay, I think this commit is quite nice. So using separate data structures allows us to distinguish between the automatons capabilities. Okay, sure. So now I'm basically trying to eliminate allocations, direct allocations as we do here. So I don't really free anything right now. I think I'm just going to allocate it in the arena, which I think we have it. We don't have our arena here. Oh yes, we have it. Or can't I just arena construct? I can. So just using our arena to allocate. So then I don't need to free, since everything is freed at once at the end. But I have to introduce a constructor. So so I'm just newing another time here. So let's also use arena. We don't have the arena here. Where do I use this? What? Should I just change this code a little bit? So basically I copy pasted this code. So basically this code and this code is the same, except this one flags the state as a start state. So can I collapse those cases somehow? So I think I can. So if I'm just, here the difference is I'm just flagging it as a start state, so fine. What if I just return not the DFA state, but set of NFA states to this DFR start state? So just return this. And then I can do the following. So those are so now reachable by epsilon. I have to do the epsilon reachability analysis, and now I can just turn this one to a state. So let's just say so we create a DFA state, and we want to say a NFA create DFA state. So, and we get passed a set of NFA states. So this is what I'm going to, how I change it. So this is states, of course. So, and so basically I put this code into here. This is my plan. So reachable, I'm renaming to states. So then I need the mapping and the arena. So pass in the arena, pass in the automaton, which we are currently building, and we pass in the mapping. Mapping this one. So in this one I will skip, I think. So now and just wrap this in here. Now we have a DFA state. I need to pass in some things. Arena DFA mapping. Arena DFA mapping. So now this state now mark as a start state here. Start state, a state, no, start is like this. And then I can move everything I do here and just remove everything I do here and just say something like, so this is a not only create, but create or get, I think. So, and then I'm just saying create or get and passing in everything I need. So the arena, DFA, and the mapping. So now I can share this code, and I flag this one as a start state. Those stay the same. So I don't know if this works. No. I know why. So previously I now need to put this state in the queue. So this was previously done in the if I already removed. So of course we have to look this state. Oh, doesn't work. Does not terminate. So if mapping does not contain, I create a new state. I flag it as an error state if the state is not empty. if the state is empty, I construct a new DFA state, adding it to the mapping. And then I'm just looking it up, but I'm always looking it up. So we already know this mapping. We should just get the pointer back. So why doesn't it work? Oh, only if it was new. Yeah, I see. So we only have to add it to our list if we didn't see this before. So if the queue contains new state, if it does not contains it, we're adding it. So this should fix the problem, I hope. So this looks better. Looks like our automaton from the beginning. Okay, sure. So what did we actually do now? Moved some code around. Yeah, two more things. So we reuse some code and we use some allocated some on the in the arena. So share some code and allocate FA states instances using arena. Do you want to have some cuddles? Or do you want to help? So cat-driven development, I think. So let's call it cat-driven pause. So okay, sure. So now I would like to do all allocations in an arena. So we have a clean slate, haven't we? Yes. So what happens if for example, if my list gets a pointer to an allocator? So what multiple? Hey, don't fight. You two. Hey. Cats are fighting on my desk. Come on. Okay. Fine. So to make this possible, we have to remember pointer to an allocator, but also we have well, inline storage would also be great. So then I could no, let's work on allocators. So for example, but what happens if I move a list, do some things with it? So how does it work? maybe let's don't do this. Maybe let's treat lists differently. So I think I'm not allocating much, reallocating lists really much. Yeah, well, a couple of times I think, but should not be that bad. I'm doing a lot more allocations of regular expression trees and also for the states and the arcs. So maybe this is fine. I'm just keeping this to do. So let's skip this for now, since yeah, I've already done this with this commit. So let's amend implementing this to do in the last commit. And while we are at it, I'm also writing this one lowercase. So now let's label accepting states. This can be done really easy now, since our DFA is a separate data structure. I can just attach some information about the accepting. So the type, if it is accepting, let's just attach a token index. So the token index. And let's assign 64-bit integer so that we can create a dummy, have a dummy value, which basically means unset. So, and now have a DFA, we set a DFA accepting this case. Then we can also set which token it accepts. We have this information here. So let's collect all tokens which are accepting. So let's say list. So let's see, we are iterating over all NFA states to make up the DFA state. So and a DFA state so I think, what do we have to do now? So we have to remember each NFA state is accepting in the order. So let's say we make a list of NFA automatons accepting, and then we're just, if they are accepting, we're just collecting them. But let's not copy them, let's just keep them by reference. So NFA state. So if our NFA state is accepting, we are remembering the automaton. So this one can be done afterwards. So then we don't skip this. we collect everything, then we do this. So what we basically have to do, if accepting non-empty, then it is accepting. So now the code should do the same thing as before, but now we also have inside of a loop. So I don't want this. I think I removed a parentheses. So let's go back a few steps. So does it compile now? No. Already it doesn't compile. Yeah, I think I know what the problem was. So if accepting non-empty, then this. So does it compile? Does it run? Does it still work? So seems like it works. Okay, so now also have knowledge which states we're accepting. So, and do we know the token? Don't know if we know this. But we implicitly know that we create the list of NFAs in the same order tokens were specified. So I think we're just going to abuse this fact. So we now get a list of okay. So we collect this. Let's see. We mark it as accepting, but also we want to write the token index. So this field we also want to write. So now we have to figure out which token automaton accepts. Well, I think it is just have to find this index. So the smallest index within the list or something like this. So small. So what do we get as a parameter? So we don't need to write anything. So I'm just changing this to const. So let's see what we have to do. We have this list of states, and we have to match it to find the smallest index in this list. So I'm thinking of creating a helper method. So smallest index within like this. So and then I'm giving it the NFAs and the accepting. And then I'm creating, all we have to do is to implement this method. So static s64, and we pass it a list of NFAs, a list of pointers to automatons. And this one, how was this one called? It was called accepting. Accept. So now for each accepting state, NFA in accepting. Now we have to find the index in this list. So current index, let's just initialize it with a senseless value. And then let's just index I, a plus I. So now if NF is I, the pointer to this is equal to the NFA we're looking at, then we remember the current index being I, and we can break in our loop. So now we found the index. So let's say assert current index is if it is valid. So I require that the index is valid. So in this case, we have to remember the smallest index. We're going to initialize by std numeric limits of S64, the maximum value, and then we can just smallest index is equal to std min of the old smallest and the current index. And then we found the smallest index, this list. So we go through all of the automatons in this list, and we find for each of those pointers the index of the automaton in this list, and we do this for every pointer in here and remember the smallest one. I think this should be fine. So, and this is the token we accept. So my cat has hungry. I think better take a break soon and give him something to eat. Let's for now just include algorithm to get std min. But we could also implement this ourselves, but I don't really care right now. So and I think this one cries because it's a type mismatch, so we're just using signed integers here, so this should be fine. So and this is of course only possible because we don't reallocate this list at this point anymore. So of course, if we search a pointer in a list which gets reallocated, then the pointers might be relocated. So the data is relocated. But in this case, it is fine, since when we use this method, this function, so it is a function, yeah. So if create a DFA, the list of NFAs doesn't get mutated anymore. So this is why this operation is fine. Okay, so now we have a DFA. Let's also print so we have a DFA. So if our state is accepting, let's print the token index as well. State.token index. So of course we have no way to print the token indices yet. This didn't really, yeah, it worked. We just can't differentiate it. Oh, hey, hi cat, what you doing? So I'm thinking just to print it as such. So using a comma. So now each accepting state is labeled with the token it accepts. So let's open our. So let's do the following thing just to make it the life a little bit easy for us. Can I somehow? Seven, 8, and of course I'm a dum-dum, and I should have done this. Since indices are 0 based in this case, so now we should see which token. Now I think we can just read it. So if we are in the start state 0 and we see an open parentheses, which we accept with token 3. Token 3, so the first is the state, the first number, and the second is the token. So if we see a white space change to character, we transition to state 2 and accept token 7. Token 7 is white space. The open parentheses transition in state 3 and accept with token 3 open parentheses. Same as closing parentheses. Star is 1, for example. And I think this should also fix our problem, since we fall back to the ordering in which our automatons are defined. So, for example, if we now have conflicting symbols such as identifier, let's use a more prominent example. So, for example, I now define a keyword called if. Let's update our labels. So keyword if and identifier are basically ambiguous, since this pattern also includes if. But since keyword if is defined first, this has the priority, and the algorithm we implemented here, the smallest index within, this should solve the problem and always use the first definition. So let's try it. Follow the trail. So in this transition, the I is exclusive, since if we transition the letter I, we can't differentiate the next token just by seeing the first I we see. So this is why this range doesn't include the I, since if you see an A and say already we are parsing an identifier, but if you're seeing an I, we can't do this. So state 10 will differentiate between keyword if and identifier, I think. But I, of course, is a valid identifier. So if we would accept in this state, we would accept and see an identifier. So let's follow the trail and see what our 10th state does. So if we then see a letter which is valid for any other identifier except F, so F is excluded here. So I think F will differentiate. So we see this here. So we already saw an I. So now we are in state 13, and if we would accept, we would accept with token 6, and token 6 is if keyword. So this algorithm differentiates ambiguous tokens and chooses the first one. And I think this is what we like. So I think now we are almost at a point. Of course, we have a lot of things to optimize and to test, but I think at the next time we can already simulate our automaton and with this do some testing. So I think we are doing this one at the next time. Yeah, so I'm quite pleased. So this was a little cleanup, but we also did some great things. So especially the labeling, which also deals with ambiguous tokens. And yeah, so maybe let's just commit everything. So I'm going to commit the main file as well as a small just to also make a copy of it, a snapshot basically. First token with patterns and this. So let's learn some English. Is this spelled correctly? So ambiguous. Okay. Okay, na gut. Well, sure. Okay, ambiguous. Fine. So now we label accepting states of our DFA with the token they accept. If patterns are ambiguous, like if and we accept, how do I say this? If patterns are ambiguous, like if and identifier, we fall back the accepting state will be labeled using the token which was defined earlier. Yeah, so I think this should be it. I think it won't explain anything more. I think it is fine. So I'm quite pleased. We are almost done. Some testing and yeah, I think and I think we can just throw some code at it, I think. So maybe just a smaller language. So I'm just hacking here the example as I need it, but I think so. Let's build a small calculator or a lambda calculus using this stuff. So just for tokenization, of course. I don't want to build an interpreter yet, but yeah. So this is a really great change, I think. We're getting close. Of course, a lot of things to do, especially if we want to create a tool which uses this library. So currently, of course, it is only a library, and the scanner is configured using code, but nevertheless, I love it. It works great, and we did some great progress today. So thank you for watching, especially if you took your time and came to this point. And I hope you enjoyed what you saw. And yeah, thanks for watching. See you next time. Bye.